Hello friends, welcome to my YouTube channel. In the previous session, we have discussed the per unit system, and now we will try to solve some problems based on per unit system. So in this session, we will discuss the important methods of solving per unit problems. The first question on the screen that we have here is: an alternator is rated at 100 MVA 11 kV and X is equal to 1.2 per unit. What will be the per unit reactance at 250 MVA and 13.2 kV? So the formula that we are going to use here is so X per unit new is equal to X per unit old into MVA new divided by MVA old into kV base whole square old divided by kVb new whole square. So based on this formula, what is our X per unit old is? It is nothing but it is 1.2, and MVA new here is the value is 250 is a new value, and here MVA old is 100 MVA. Now kVb old whole square is, it is nothing but it's 11 kV, and this one is 13.2. so we'll substitute this formula here. So X per unit new is equal to old value is 1.2 into 250 divided by 100 into 11 whole square divided by 13.2 whole square. So if you solve this equation, you will get this one as 2.08 per unit. So important conclusion here is the per unit values may be greater than 1, less than 1, equal to 1, but it is always positive values only. That is a conclusion that we can observe. And the second question on the screen, the alternator is rated as 200 MVA 13.2 kilovolts and X is equal to 6 ohms, and what will be the per unit reactance at new values? So in this case, first we have to take this one as an old value, that is SB old, and this one is VB old values, and this is the actual value. Now first we have to convert these values into per unit values. So we use the previous formula only. So X per unit is equal to, so X in ohms into S base divided by VB square. So this is the formula. We want to convert the actual values into per unit values. It is derived from X per unit is equal to X actual value in ohms divided by X base values. So X base value, we found this one as this one. So X base is S base divided by VB square. So you can go through my previous lecture how we derived this. Now this is equal to X means ohm is 6 ohms into S base is, it is nothing but 200 divided by 13.2 whole square. So if we solve this, we will get as 6.88 per unit. Now we will use second formula, that is X per unit new is equal to X per unit old into MVA or SB new divided by MVA old into kVb old square divided by kVb new square. So here, what are the new values and old values? So X per unit old is nothing but 6.88, and MVA new is, what is the MVA new value? Which is 400 MVA, and MVA old is 200, and kVb old whole square. So which is the old value? It is 13.2, and this one is kVb new is 18.2. So if you substitute these values here, it is nothing but 6.88 into 400 by 200 into 13.2 whole square divided by 18.2 whole square. So we'll solve this, we'll get as 7.25 per unit. So next we'll try to solve a new problem here. So here a 100 MVA 33 kV 3-phase alternator has XT double dash, means it's a subtraction reactance is 15%. So it is equivalent to, this value is equivalent to 0.15 per unit, and alternator is connected to the motors through a transmission line transformer as shown here. Below the select the generator base quantities. So select the generator base quantities, calculate the per unit values for other equipments, and also draw the single line diagram here. So this is a question asked in IAS. Now the procedure is select the common MVA base for the entire network, and second, the system is divided into number of sections. So number of sections based on what? Based on transformation, as we discussed earlier. So here we will divide into three sections here. So this is the section number 1, and from here to here, because until the transformer is in, so section number 2, and from here to here till the load is section number 3. We have divided. So transformation, based on transformation ratio, we are going to calculate the base voltages. So calculate the per unit values of voltage and impedances each section and connect them as per the topology to get the single line diagram. So here friends, what we are doing here is we are going to take this network. The network is divided into three sections based on its transformers. Because in the transformer only the voltage is going to be changed. So based on that we are going to change the divide the network into three parts here based on transformers. Now we will take each part and we will calculate the base value and its per unit values as shown below. So as per the given data, the base values are, select the generator base values. So now I will get the values as SB. So new value is 100 MVA, and VB new value is 33 kV. Now I want to find what is the per unit reactance, new value of per unit reactance here. So I will use the previous formula here. I will use this formula for all the calculations. So X per unit new is equal to X per unit volt into MVA new divided by MVA old into KVB old square divided by KVB new. So I will take the first case. So this is the entire network, first network here. So first network, during the network, so X per unit new value is equal to X per value old value is 0.15 into MVA new value. So new value and both the same only. So 100 by 100 into VB is 33 divided by 33 whole square. So we'll get a 0.15 per unit only. So this is the per unit reactance of our alternator. So we'll choose the second network. So when we are going from here to here, there is a voltage change here. So the voltage changing from 32 to 110 kV. So this is the major reason for doing a lot of calculations in absolute per unit systems. So in order to avoid that, we will choose the per unit systems here. So how we are going to do the calculations here? So by choosing the base values. So formula that we are going to use here is, it is V2 base divided by V1 base is equal to transformation ratio K is nothing but V2 by V1. So now here the no voltage change occurs here. So I will take this one as transformer as a two sections. So XT1 is a primary side and here we have secondary side. Let's say so primary and this one is secondary. So transformer calculations on primary side. So transformer, I will take this one as XT primary. So XT old value, what is the old value? They have mentioned 8%, that means 0.08. So into MVA new by MVA old. What is the MVA new value? It's 100. MVA old is 110. So MVA new is 100 divided by MVA old is 110. So here 110 is given into KVB old square. So what is the KVB old value? So old value means nothing but specified value here. It is 32 whole square divided by 33 is a base value, new base value, right? Square. So you will here you will get 0.0684 per unit. Suppose if I go for X unit XT secondary. Now So here the voltage levels are changing in the given problem. Okay, so here the primary is 32 but secondary is 110 kV. So based on this formula we are going to find what is a V2 base value here. So I want V2B here. What is a V2B? So V2B is equal to, what is the primary side base voltage? It is nothing but 133 kV. Okay, so V2B is equal to 110 is a secondary side voltage divided by V1 is 32 into what is the V1 base? V1 base is 33 kV here. So 33 is equal to how much you get? It is nothing but 113.4375 volts. So this is the voltage that we got here. Okay, so these are in kVs. Now what are the base values here? Exponent volt is equal to, so 0. It will remain same only, 0.08 into MV and U by MVA volt. So MV and U is 100 divided by 110. So here V2 kVB old value. So what is the kVB old value here? On the secondary side it is nothing but 110 volts is a old value. Okay, so here I will take 110 as a old value referred to secondary side of transformer. Sorry, 110 here. So 110 divided by how much we got? 113.43. 113.43 whole square and this one whole square. So if you solve this, 0.684 per unit. So conclusion here is what we got in per units. We have seen that in per unit system, the XT primary in per unit is equal to XT secondary in per unit. So that is what we can observe here. Next we calculate for transmission lines. So in the transmission line here, it is represented in ohms. So we like to find the per unit values of this transmission line in per units. So the formula that we will use here is, that is X per unit is equal to X actual value in ohms divided into MVA base divided by kV base whole square. What is the base value here? It is nothing but just we found 113.43 is the base value. So V base here, and the actual base of the transmission system is, it is 100 MVA. So these are the base values for this system. Now we will go to the solutions. Now for transmission line, XTL is equal to, so actual value is in 50 ohms, 50 into base is 100 divided by voltage is 113.43 whole square. So this is the 0.3886 per unit. So this is the value of transmission line per unit reactance. And here next we will follow the same procedure for the entire network here. So here also network 2 is completed. Now we are going for network 3. So for this network 2 here, so this is the transformer 2. Okay, so here its voltage is 110 volts. It's a base value, right? So now I'll write the formula. So XT primary side is equal to, it is nothing but 0.08 into MVA and U is 100 only. MVA base is, what's the base value here? See that we found is 113.43 here. It's a primary side base. Okay, so 113.43 whole square. So that you will get it as 0.0684 per unit as is same. And next we will going to find XT per unit secondary side. So XT secondary. So before going to do secondary here, I will take that V2 base divided by V1 base is equal to transformation ratio K is nothing but V2 by V1. So V2 is 32, V1 is 110. So this is the one. Now alright, so V2B is equal to, what's the V1 base value? It is nothing but 113. So 113.43 into 32 divided by 110. If you solve this, you will get approximately as 33 kV. So this is the new base value. Now XT secondary is nothing but 0.08 into 100 divided by new base value, MVA value is 110 into kV base is 32 old square. So this is the old value 32 here, and a new value that we got is 33 whole square. So solve this, you will get the 0.0684. So you can observe here also in per unit system, the transformer primary and secondary both are having same units. So that is what conclusion here. So this part is over. Now what is the base voltage here? So here we got is 33 kV. So any mistake here? So 33 kV given problem, right? So 33 kV is the output voltage. Now we'll solve for these motors. So once again, sorry here, I made a mistake. So these are 32 kV, and this is 32 kV in the given problem. Okay, now we'll go for the motors. So for motors, the motors will be XM1, which is nothing but per unit old value. So 20% means 0.2 into MVA new. MVA new value is 100 MVA, and old value here is 30 into kVA old value is 33 and kVA new. So kVA old value is how much? Sorry, 32 here. So 32 whole square divided by 33 whole square. So we'll get it as 0.551. So for XM2 for secondary motor, what's the per unit reactance? This is 0.2 per unit into 100 divided by, now the MVA is 20, so 20 into kVB old value. So kVB old value is how much? 32 only. So 32 divided by kV new is 33 whole square. So we'll get it as 0.8264. Similarly, we'll get XM3, it has 0.33 per unit. Okay, so we'll draw the single line diagram here. So in the previous session, we discussed how to draw the single line diagram for various equipment such as transformers, transmission lines, and motors. So according to that, we will draw it. The alternate can be represented as a voltage source. It is represented as EG here. So it is by default it is a 1 per unit value, and we are going to specify its reactance. What is a new reactance? X per unit new values, it is nothing but 0.15 is a new reactance. It is nothing but XT double dash. So this part is completed for that alternator. So now we'll go to the transmission lines. So transformer, sorry. In transformers, we will take the reactance of the transformer like this. It is how much it is? It is nothing but 0.0684 per unit. So with this, transformer part is over. Next we have transmission line. So transmission line, so this is transformer 1, and next transmission line here. So this is transmission line. So J is 50 ohms. So per unit, how much you got? So 0.3886 per unit. So with this, transmission line is also over. Next thing is transformer 2. So transformer 2 here, how much you got? Same 0.0684 per unit. So till this part is over. Now these three loads are in parallel. So motor M1, M2, M3. So how will represent this motors here? So we'll represent the motors same as like inductive loads. So here, so the new reactance of the motor 1. So we'll represent M1 here. So M2, M3. So what is the M1 here? How much we got? So 0.0, sorry, 0.551, 0.82 and 0.33 reactance here. So all are represented J because it's our reactances. So J, J, J here. So this is the per unit reactance diagram for this entire network. So next type of problems here is draw the per unit equivalent circuit reactance network for the following network. Choose 100 MVA and 132 kV as a transmission line. So transmission line base values are given. That means they have specified for these transformers V2B is what and V1B is what here. Okay, we need to find the other components here. So here first we'll take base voltages here. So what is our voltage for generator? So V2B is equal to K2 mean K into V1B. So what is the K? Is nothing but for transformer, for say generator 1. Generator 1, what you will get? So transformer is here. So K is nothing but, what is this value? 132 divided by V2 by V1. So V2 by V1 here. So K value. So what is V2B base value here? What is V1 base I want to find here? So only we know V2B. So I want to find what is V1B. So V1B is equal to, so what you can write is V2B by K. So what is V2B that are specified? That is 132 kV divided by K value is 132 into 11. So here we have base value of 11 kV. So this is the V1B. Here is it's 11 kV, the transformer primary side. Okay. So similarly we have generator 2 here. So generator 2. So here we are going to calculate. Generator 2 also same formula. So they were specified V1B and we need to find V2B. So V2B is equal to K into V1B. What is the K? So K is nothing but it is 13.8 divided by 132 into what's the V1 base value? They have been spared. It's 132. So it is nothing but 13.8 kV. Okay. So this is the given data. So per unit values with respect to base values, we're going to calculate for each and every component. So now we'll calculate for a generator 1. So for generator 1 we are going to calculate. Okay, so xg1 is equal to xg old value, so 0.15. What is the MVA new value of the transmission line? Is nothing but 100. So existing value is also 100. So 100 into MVA new divided by MVA voltage. What is the base voltage here? 11 kV. So existing voltage 11 kV. So 11 divided by 11 whole square, you will get it has same value as 0.15 per unit. Similarly, we will go for xg2. So xg2 is nothing but it is having a per unit reactance of 0.2 into what's its old value. MVA old is MVA new value is 100. MVA old value is 200 here. So divided by 200 into what is KVB old value. So KVB old value is 13.8. A new value at this point here is base 2 values here is 13.8. So 13.8 divided by 13.8 whole square, you will get the same value it as 0.1 per unit. So these are the with respect to generator 1, generator 2. So similarly we will go for transformers. So for transformer XT1, the primary side. So XT primary is equal to the actual per unit value is 0.1 into MVA old value. What is MVA new value? Sorry, here MVA new value is 100. MVA old is 120 into KVB old value. So old value here is, and primary side is 11 only. So 11 divided by 11 whole square. You will get it as 0.0833. So similarly, XT secondary. So here XT secondary is XT per unit 0.1 into MVA new value is 100, MVA old value is 120 into KVB old. So KVB old value here is, what is the secondary side KVB old value? The transformer. So here KVB old value is 132 kV divided by new value is 132. So whole square, which is all this 0.0833. So per unit values, all are per unit. So similarly you can solve for the transformer T2. So XT2 of secondary transformer, second transformer, so which is here, so which is equal to, so 0.1 as a per unit value into 100 divided by 250 MVA into KVB old is 13.8 whole square divided by KVB new is 13.8 whole square. So we will get as 0.04. So this is for same for primary and same for secondary per unit values. So next case we will consider here the transmission lines 1 and 2 and 3 here. So for transmission lines, R per unit is equal to R in actual values into MVA base by KVB whole square is the formula, and X per unit is equal to X ohms divided into MVA base divided by KVB square is the formula. For transmission line 2R, so both the values are identical, so we'll take the transmission line 2 and transmission line 3 same values. So transmission line, resistance of transmission line 2 is nothing but resistance of transmission line. So they are form of R plus Jx palm here. So resistance is 25 into 100 into 132 square. So we'll get 0.143, and similarly RT2 also, it's a 25 into 2 means 50. So we'll get this answer. Similarly, X transmission line, the reactance of transmission line 2 and 3 are both the same. So 100, 100. So base value is 100 and kV value is 132. So like this we can find the transmission line 2. So when the loads are in parallel, this is the formulas. So when the loads are in parallel, S base divided by S into cos theta. In the problem given is S base and cos theta, S base and S cos theta. So cos theta is 0.8, sin theta is 0.6. And similarly you can find the Z per unit based on the formula here. So based on the S base formula, Z per unit is equal to, so based on this formula, Z per unit is equal to S base divided by S into cos theta plus J sin theta. In the given problem, this power factor plus J sin theta is nothing but cos theta is 0.8, sin theta is 0.6 here, and S base is 100, S is 250 in the given problem. Okay, so here Z per unit is equal to complex conjugate of these values. So the complex conjugate of this is 0.32 plus J 0.24. All are in per unit values. So from this, R load is equal to per unit is 0.32 and X load is 0.24. So thank you. If you like my videos, please subscribe, comment. Thank you.